Somewhere in Texas, 33 rocket engines are about to ignite at the exact same instant. Each one runs at 350 bar of pressure. That is more than enough to crush any submarine ever built, several times over. And if a single one of these engines lights up even a fraction of a second out of sequence, the disturbance can ripple through the whole machine in milliseconds. This is the Raptor. It may be the most complex engine humanity has ever fired. And the strangest part is that by almost every old rule of rocket engineering, it should not work at all. For decades, engineers treated the cycle inside the Raptor as a trap. It had been attempted only a handful of times in history, and nearly every attempt ended in fire, failure, or quiet abandonment. Powerful space agencies with enormous budgets studied it, ran the numbers, and walked away. And yet, SpaceX did not just build one. They built hundreds. They bolted 33 of them to the base of the largest flying object ever made and lit them all together. So the question I want to answer today is easy to ask and very hard to answer. How does the Raptor actually work? Why is it so dangerous? And why, out of every possible design, did this violent, nearly impossible machine turn out to be the one engine that could carry us to Mars? Stay with me, because by the end of this, you will understand three things. You will understand why the Raptor runs at more than 3 times the chamber pressure of SpaceX's earlier engine, and how it keeps that pressure from tearing itself apart. You will understand the cycle that defeated everyone who tried it before, called full-flow staged combustion, and why methane is the only fuel that lets it survive. And you will understand the part almost nobody mentions, that the Raptor was never designed for one planet. It was designed for 2. To understand any of that, we have to start simple, and then watch it get harder, one layer at a time. Let's begin with the basics. Strip away the complexity, and every rocket engine does the same thing. You have a tank of fuel and a tank of oxygen. You pump them both into a chamber. You ignite them. The burning gas has nowhere to go but out through a nozzle at the bottom, and as it rushes downward, the engine is pushed upward. That is thrust. Newton's third law, written in fire. But here is the catch that shapes everything that follows. To get real power, you have to force the propellant into the chamber at enormous pressure. And to make that pressure, you need pumps. Not ordinary pumps, but monstrous turbopumps spinning tens of thousands of times a minute. The real question of rocket design is not how you burn the fuel. It is how you power the pumps that feed the fire. The simplest answer is to burn a little of your propellant in a small side chamber, use the hot gas to spin a turbine, let that turbine drive the pumps, and then throw the gas away out a pipe on the side. This is called an open cycle, and it is exactly how SpaceX's first engine, the Merlin, works. To understand why the Raptor exists, you first have to understand why the Merlin was brilliant and where it hit a wall. 20 years ago, SpaceX had a very different problem. The money was finite, the credibility was zero, and the company needed an engine that was cheap, simple, and reliable enough to reach orbit at all. The Merlin was the answer. It burned a refined kerosene called RP1 with liquid oxygen. Kerosene is cheap, dense, easy to store at room temperature, and it had been proven for half a century. The open cycle design was old and well understood. The Merlin became one of the most reliable engines ever flown, and it still launches Falcon 9 today. But the Merlin has a ceiling that almost nobody talks about. Kerosene is a heavy, tangled molecule, a long chain of carbon and hydrogen. When it burns, it does not burn cleanly. It leaves behind solid carbon, a black residue called soot. Engineers have a word for what happens when that residue builds up inside an engine: coking. For a rocket, you fly once and discard, coking does not matter. But imagine an engine you want to fly again the next morning, and the morning after that. The soot has to be cleaned out. The engine has to be inspected, serviced, reset. Rapid reuse, the kind where the same engine flies again and again with almost no work in between, becomes a nightmare. And there is a second limit. An open cycle throws away some of its propellant out, that side pipe, which caps how high you can push the chamber pressure, and therefore how much thrust you can wring out of every kilogram of engine. Then Elon Musk described the next mission, and that mission broke the Merlin completely. He wanted Starship, the largest rocket ever built, lifting itself off the pad on 33 engines, landing itself, refueling, and flying again, ideally on the same day. No engine in existence could do that. Not the Merlin, with its coking. Not the space shuttle's main engines, which were magnificent but enormously complex and never built for rapid turnaround. Nothing. The mission demanded an engine that did not exist. And that forced SpaceX to ask a much deeper question. What if the fuel itself was the problem? This is where methane enters the story, and where the whole design starts to make sense. Methane is the simplest hydrocarbon there is. 1 carbon atom, 4 hydrogen atoms, the same gas that heats homes around the world. Because it is so simple, it burns almost completely. Its only real products are carbon dioxide and water vapor, both gases that flow straight out of the engine. There is essentially no soot, no coking, nothing to clean. An engine that burns methane can, in principle, be fired again and again without being torn down in between. But chemistry is only half the story. Both methane and oxygen have to be carried as super-cold liquids. Methane turns liquid at about -161 degrees Celsius. Oxygen turns liquid at about -183. The Raptor burns them at a mixture ratio of roughly 3.5 to 1 by mass, oxygen to methane, flooding hundreds of kilograms of propellant through the engine every single second. That clean burn is what unlocks the door, because a fuel that leaves no residue is the one fuel that lets you close the cycle. Instead of throwing the turbine exhaust away, you can send all of it forward into the main chamber. Nothing wasted, every gram of propellant contributing to thrust. With kerosene, that closed design would quickly clog itself to death. With methane, it becomes possible. And that closed design has a name: full-flow staged combustion, the cycle that beat everyone before SpaceX. Now watch closely, because here is the heart of the machine and the source of its danger. In the Raptor, the propellant does not go straight into the main chamber. It first passes through 2 small combustion chambers called pre-burners. And this is the detail most people get wrong. So let me be precise. There are 2 of them, and they are deliberately unbalanced in opposite directions. One pre-burner burns a tiny amount of methane with a large flood of oxygen. That is the oxygen-rich pre-burner, and the hot gas it makes spins the turbine that drives the oxygen pump. The other pre-burner does the mirror image, a tiny amount of oxygen with a large flow of methane. That is the fuel-rich pre-burner, and it drives the methane pump. Here is why they run lopsided instead of burning evenly. If you burned the propellant completely inside a pre-burner, the temperature would instantly destroy the turbine blades. So you starve the burn on purpose. The goal is not heat. The goal is pressure, just enough expanding gas to drive a turbine without melting it. And now the trap reveals itself. Each pre-burner powers the pump, but the pump feeds the pre-burner. The thing that spins the turbine is created by the turbine it spins. It is a loop that feeds itself. Speed up the pump, and you raise the pressure that speeds up the pump even more. The Raptor lives by forcing this self-reinforcing loop into a stable balance at staggering pressures, on the order of 350 bar in the main chamber and even higher inside the pumps. When it works, it is the most efficient way to burn a rocket. When it drifts, it can run away in milliseconds. Imagine balancing a pencil on its tip while the floor keeps shaking. That is the Raptor every second it runs. There is one more piece of genius buried in here. Before the cold methane ever reaches its preburner, it is routed through channels in the walls of the nozzle and chamber, soaking up the ferocious heat of combustion. This does two jobs at once. It keeps the metal from melting, and it warms the methane into the perfect state to burn. The fuel cools the engine on its way to becoming the thing that powers it. After the preburners, both streams arrive at the main chamber as hot gas, one oxygen-rich, one fuel-rich. They finally meet and burn together completely, and only now is the full energy released. Two staged combustion events in a single engine, weak ones in the preburners to make pressure, a violent one in the chamber to make thrust. That is what staged combustion means, and full flow means both propellants pass entirely through the system with nothing dumped overboard. So how do you even light something this volatile? Here is where I have to correct a myth you may have heard, that the launch tower spins the engines up from the outside. It does not. The Raptor lights itself using dual redundant torch igniters, small spark-lit methalox flames like the pilot light on a stove that ignite each preburner from within. There is no field of pyrophoric chemicals as the Merlin uses because a reusable engine cannot rely on a limited supply of one-shot igniter fluid. Spark plugs are inert and endless. That is what makes restarting in flight, and one day on another planet, even thinkable. Now you can finally see why the Raptor is so dangerous, and why that danger is the point. Two coupled feedback loops, each balanced at extreme pressure, both of which must stay perfectly synchronized. If the oxygen turbine slows even slightly, its pump slows, its preburner loses pressure, the turbine slows further, and the cascade builds on itself. The methane side can do the same thing independently. If the two drift out of step, the pressures inside the engine go asymmetric, and asymmetric stress at 350 bar does not forgive. SpaceX manages this with sensors watching pressures continuously and a control system that can shut an engine down in an instant if anything wanders. The volatility is real. It is not exaggeration. So why accept it? Because nothing else can do the job, and because of where this engine is ultimately going. Look at the alternatives, and each one fails in its own way. The mighty F-1 that powered the Saturn V was a single-use giant, far too heavy and fragile to ever land and fly again. The space shuttle's main engines were closed-cycle marvels, but they were inspected and hand-tended after every mission, the opposite of rapid reuse. And the Merlin, for all its reliability, still chokes slowly on its own soot. Every existing path led to a dead end. Only a closed cycle gives the efficiency Starship needs. Only methane allows the closed cycle to survive repeated reuse. Only 3 engines in history have ever flown full-flow staged combustion at all, and the Raptor is the one that did it at scale. But the deepest reason is Mars. You cannot haul kerosene across the solar system. It is too heavy, and there is none waiting there. Mars, however, has an atmosphere that is almost entirely carbon dioxide. Using a known chemical process, combined with water ice, you can manufacture methane and oxygen on the surface of Mars itself. The same propellant, the same engine, a rocket that can refuel on another world. The Raptor's fuel was not chosen only to launch from Earth. It was chosen so the engine could one day come home from somewhere else. Think about what that means. The volatility you have been hearing about is not a flaw the engineers failed to remove. It is the signature of the only design that solves an impossible set of demands at once. Powerful enough to lift a skyscraper, small enough to pack 33 into one booster, clean enough to fly again tomorrow, and chemically able to be made on Mars. Take away any one of those, and you no longer have the Raptor. At the start, I told you that 33 of these engines light together, and that being a fraction of a second out of step could ripple through the machine. You now know exactly why that is true, and why SpaceX accepts the risk anyway. It is not a design that went wrong. It is the price of solving a problem that, by the old rules, should not have had a solution at all. And maybe that is the real lesson here. Sometimes the most dangerous tool is also the most necessary one, and the complexity is not a mistake, it is the answer. Getting to Mars was never going to happen with a safe, simple engine. It happens with an engine like this. So here is what I want from you before you go. Tell me in the comments which part of the Raptor surprised you most, the two pre-burners, the self-feeding loop, or the fuel made on Mars. And if you want the next piece of this story, stay close, because next we will trace exactly how 33 of these engines light in under a second without tearing the rocket apart.